Get down.
So what are we really looking at here? F is that drag force we're trying to figure out. That Greek letter 8s stands for the fluid's viscosity, its thickness, so honey has a way higher viscosity than air. R is just the radius or the size of our object, like our little steel balls, and V, well, that's its velocity, how fast it's going.
So here's the crucial takeaway. The drag force isn't some constant number. It gets stronger if the fluid is thicker, or if the object is bigger, or, and this is the absolute key to our whole mystery, if the object is moving faster. The faster you go, the harder that fluid pushes back on you.
And this brings us right to the climax of the story. We've got these two forces going at it, gravity pulling everything down, and this drag force pushing everything up. So, what happens when they finally meet?
I want you to picture it like a tug of war. On one side, you have the pull of gravity on our falling object. That force is constant. It doesn't change. But on the other side, you have the drag force. It starts at 0, and it grows stronger and stronger and stronger as the object speeds up. Sooner or later, something's got to give.
Let's just walk through it. First, you drop the object. Gravity grabs it, and it starts to accelerate. As its speed picks up, that viscous drag force gets bigger and bigger. And then you hit this magic moment where the upward push of drag becomes exactly equal to the downward pull of gravity. The forces are perfectly balanced. And at that exact moment, acceleration just stops, dead in its tracks.
And that final constant speed, it has a name. It's called terminal velocity. It is the absolute maximum speed an object can reach when it's falling through a fluid. It's literally the speed limit imposed by the laws of physics.
Okay, time for the big payoff. Let's see Stokes' law in action. We've gone from a rainy day to a honey jar to a physics formula. Now, let's put it all together and finally solve our original puzzle.
And there you have it. Air, as thin and empty as it feels to us, is a fluid. As a raindrop falls and speeds up, the drag force from the air pushes back harder and harder until it perfectly balances the force of gravity. The raindrop hits its terminal velocity, a speed that's, pretty fast, but thankfully not bullet fast.
And believe me, this idea goes so far beyond just the weather. Understanding Stokes' law is absolutely crucial in tons of different fields. It helps meteorologists model how clouds form. It helps engineers design the perfect paint that doesn't drip. It helps doctors understand blood flow. And it's used to separate tiny particles in industrial processes. This one simple idea has applications that are just incredibly wide-ranging.
So if you need the one line, cram for the exam takeaway, this is it. Stokes' law is the key that unlocks the whole relationship between a fluid, an object, and the forces that control how they move. It's the simple, elegant reason